Welcome everyone. Today we're discussing the integration of robots and drones in industrial maintenance. The core philosophy of this session is simple. We want to remove people from hazards, but we must never remove them from the decision-making process. We'll explore how to balance automation with human oversight to ensure safety and data quality. Let's start with a reality check. Imagine a drone completing a complex flight inside a dark boiler house. It returns safely, and the team is thrilled until the engineers look at the footage. They find the angles are wrong, there's no sense of scale, and they can't match the anomalies to specific locations. The flight was a success, but the inspection was a failure. This highlights our central question. What must a mission prove beyond just a successful flight? From a practitioner's view, why does this matter? Robotics only adds value when it collects decision-grade evidence. We must prioritize mission before machine. This means starting with the hazard and the failure mode rather than the cool factor of a new gadget. We also have to be mindful that while we reduce old risks like heights, we introduce new ones like battery safety and wireless interference. By the end of this session, you should be able to select use cases based on hazard reduction, write clear data quality criteria, and build a robust authorization process. We want to move from a pilot mindset to a production mindset where every inspection is integrated into your work order system and measured for its real business value. In our first section, we're going to look at risk. To manage it, we first have to see the system conditions that transform ordinary maintenance work into enterprise-level risk. Before we dive into technical solutions, we need a shared language. For instance, autonomy isn't just a robot moving on its own. It's the degree to which navigation or interpretation happens without real-time control. Most importantly, we need decision-grade data, evidence that is traceable and contextualized enough to authorize a million-dollar repair. When we talk about risk, the loss is often much larger than a maintenance invoice. We are trying to reduce hazard exposure in confined spaces or at heights, but we must also watch out for operational interference, the risk that the robot itself causes a plant trip or a safety incident. Failures in technology adoption usually happen in a chain. It starts with choosing a platform because it's novel, leading to weak mission design and poor data context. If there is no qualified review of that data, the chain breaks and the findings never turn into actual maintenance work. A robot mission isn't a success until the decision loop is closed. Watch out for these warning signs. Coverage gaps where the battery dies before the job is done, or data overload where you have thousands of files but no idea where they belong. The most dangerous sign is an orphan anomaly, a defect that shows up in a report but never makes it into your maintenance management system. To evaluate if your current system is real or just an intention, ask these 8 questions. Is the use case tied to a specific failure mode? Are there defined acceptance criteria? Can findings be traced to a baseline? If you can't answer these with evidence, your system isn't yet robust. Now that we understand the risks, let's move to section 2, building a disciplined operating model that ensures every mission produces actionable results. We follow 5 core principles here. We prioritize hazards first, value evidence over the spectacle of the flight, design for safe failure like loss of link protocols, maintain human judgment at decision points, and always close the work loop by integrating findings into repairs. This is the Mission 6 model. It's a 6-step process that connects hazard reduction to verified action. From selecting the mission to acting and verifying the repair, the robotic platform is just one component in a much larger engineering system. In the select phase, the asset owner is accountable. We define the hazard, identify the failure mode we're looking for, and screen for feasibility. The output here is a formal use case charter. Next, we specify. The inspection engineer must define exactly what good looks like. What is the required image resolution? What is the flight route? Without these specs, you cannot have a successful mission. In the authorized phase, operations and HSE take the lead. They set the exclusion zones, check operator competence, and approve the emergency response plan. This ensures the robot doesn't become the hazard. During collection, the operator must execute repeatably. This isn't just about flying. It's about verifying data quality in the field and tagging every piece of evidence with asset and location data. When we interpret the data, we might use AI as an aid, but a qualified human must review the findings. We compare new data against a baseline to assign a confidence level and determine the consequences of any anomalies found. Finally, we act and verify. The maintenance manager ensures that validated findings turn into prioritized work. Once the repair is done, we use the robot again to re-inspect the as-left condition to prove the work was successful. To prevent convenience from becoming bad policy, we use clear decision rules. For example, if a robot reduces exposure but the data quality is improving, you must run a paired validation against conventional methods before you fully substitute the robot for a human. In Section 3, we'll discuss how to make this model executable in the field, focusing on ownership and the rhythm of management. Reliability often fails in the gaps between departments. We need one accountable owner for each role, from the asset owner who defines value to the maintenance planner who converts anomalies into work orders. Standard work turns good intentions into repeatable results by following this 7-step sequence, including a final sustained step to audit and update the standard. You ensure the system survives beyond the first successful pilot. A control is not just training, it's a specific, observable action. This includes use case gates to score value and data traceability standards that link every file to a specific asset and sensor. We only want to capture the minimum data required to change a decision. This includes mission context, achieved coverage, sensor quality, exact localization, the diagnostic finding, and finally, the record of work closure. Measure what triggers action. Instead of just counting flights, track exposure avoided, the number of hours people were kept out of harm's way. Track the validated hit rate to see how often AI flags are actually real defects. Management cadence is how you build culture. This ranges from daily frontline reviews of exceptions to annual strategy resets where you refresh your lifecycle assumptions and priorities. Technology should reinforce existing discipline. Your software and hardware, from the sensor payload to the CMMS integration, must preserve a single, traceable chain of evidence from the field to the work order. Now, let's look at how we apply, verify, and sustain this method in a real-world scenario. Consider a vessel inspection. The team wants to avoid confined space entry. Currently, they have a drone, but weld locations aren't mapped and lighting is inconsistent. The decision point is, can this drone replace the entry, or is it just a screening tool? By applying our framework, we change the system. We specify the weld coverage and lighting requirements, authorize the operator, collect a map dataset, and have a human inspector validate the AI's findings. This turns a flight into an inspection. The verification of success is clear. Reduced exposure, documented blind spots, and findings that are traceable to specific welds. The lesson is that blind spots are not an embarrassment. They are evidence that needs to be managed. Let's try a tabletop exercise. Imagine inspecting a high stack during operation where wind and heat are factors. Ask yourself, what hazard is removed? What data quality is needed? Who validates the uncertainty? This is how you prepare for a real-world mission. Avoid these common traps. Don't buy a platform without a mission, and don't equate high image resolution with high inspection quality. If you find yourself in these traps, the recovery move is always to return to the failure mode and the required evidence. Here is a 90-day roadmap. Start by identifying hazardous tasks in the first month. Run paired validation pilots in the second. And only in the third month do you verify the repair loop and decide whether to skip. When communicating with management, present a credible business case. Balance the value of reduced exposure and shorter outages against the life cycle costs of batteries, software, and training. Value equals exposure avoided plus improved decisions minus lifecycle costs. To ensure everything is working, use this 12-point field audit. Score only what you can actually observe or trace. If there's no traceable link between a dataset and an asset, that's a gap in your system. In summary, mission before machine. Specify decision-grade data. Keep humans at the decision gates. Our commitment as leaders is no platform without a mission, no finding without context, and no automation without accountable review. For those looking to dive deeper, I've provided several resources, including standards from ISO and OSHA, and case studies on waste tank and offshore wind inspections. All industrial photography used in this presentation is sourced from open licenses, and you can follow the links to see the real-world context of these applications. I'll leave you with one action. Which hazard can you remove today without removing human judgment? Automate the exposure, but strengthen the decision. Thank you.